This is a short tutorial about practical advantages of functional programming. My approach is extremely pragmatic and not academic. This means I'm asking the question, what are practical advantages of functional programming for practicing software engineers? I am not, for instance, taking as an advantage the fact that certain constructions in functional programming are connected to category theory. This could be an advantage to an academic scientist who can then publish more papers about theory, but this may not be an advantage to a practical programmer. So this is what I mean by an extreme pragmatic and unacademic approach. What are the advantages of functional programming? We can find that features of functional programming have been added to many programming languages by now. What are these features? What are the reasons that these features have been added? The reasons are that there are specific practical advantages. Even very conservative languages such as C++ and Java have added certain features of functional programming. This must be a very significant practical reason. And I identify 4 features, which are in the order of increasing complexity and decreasing advantage. The first feature is that functional programming allows us to write iterative code without writing loops. The second advantage is that we can use functions parameterized by types, and this is all checked by the compiler. This excludes a large number of errors, such as forgetting to initialize some variable in a loop or using incorrect type in some way. The third advantage is that functional programming supports so-called disjunctive types. I will explain what that means. In this way, a programmer can model special cases, errors, and so on. It's a very powerful way of writing programs because the compiler can check that no special cases are left without being handled. And finally, functional programming proposes a special syntax that allows the programmer to write chains of effectful computations. I will explain what that means, in a syntax that makes programs very easy to read and to maintain. So now I will go through these advantages and these features in detail. I will use Scala as the programming language, but exactly the same advantages hold for many other functional programming languages. The first feature is being able to write iterative programs without writing loops. Here is an easy interview question that could be asked of a software engineer. Given an array of integers, we need to find all pairs of these integers whose sum is equal to a given number. There are solutions for this problem. For example, I'm just showing a link to a page with that solution in Java, which takes about 10 to 20 lines of code. A functional programming solution takes 1 line. For completeness, I show 2 different solutions. One solution has quadratic complexity, and the other has a complexity n log n. But they're all one-liners in functional programming. For example, in Python, you would write like this. This is a single line that computes the list of all pairs x, y, for x in the array, for y in the array, limited to the sum being equal to a given number n. In Scala, exactly the same computation is written like this. In Haskell, it is written like this. A functional programming solution with n log n complexity is written like that. You first convert arrays to sets, which is an n log n operation, and then you write a single line, which is also an n log n operation, because each time you check containment, this is potentially log n complexity. So it's n times log n. But you see that the code does not contain any kind of loop construction, any kind of index that goes from 1 to the length of the array, or any kind of incrementing the index in a loop. This code looks like an expression that evaluates to another set. So, for example, here is a set, and this expression evaluates to another set. And this, in Python, it's the same. This evaluates to a list. In Scala, this evaluates to an array or a list. So in this way, of course, when this is compiled and run, there is a loop, but you do not write that loop. You write a higher level description of what needs to be done. A similar thing happens for aggregation. An aggregation means you have a sequence or an array or a list or a set, and you need to compute a single value out of that entire list by aggregating the data in some way. Here's an example. Given an array of integers, you want to compute the sum of square roots of those integers, and you need to exclude negative ones because square roots are not going to be real numbers. So in Python, you would write a one line like this. In Scala, you would write it in a different syntax, but also a one line. Another example is that you want to compute the sum of only those integers that are not negative and whose square root is also present in the set. So you've got 15 to 20 lines of code in Java, and the functional programming solution is again a one-liner. I wrote it split between 3 lines just to make it easier to see. We have a set. We filter the set by the condition that the value is non-negative and the set contains the square root of that value, and then we compute the sum of the resulting numbers. So this is the kind of computation that replaces loops and is available in the functional programming languages. Another example is to compute a positive integer given an array of decimal digits for that integer. So you have an array, for example, 1, 2, 3, and you want to compute the integer 123 out of that array. So this is the Scala code that computes that. So again, there are no loops that are written explicitly, and this is a chain of computations that compute new collections from old ones, and eventually you have an aggregation using the sum method. So this technique, where you write chains of computations starting from one collection, then getting another collection, getting another collection, another collection, and so on. This is a very powerful way of manipulating data in collections that is much easier to deal with than writing explicit loops. This code is much easier to maintain. You can still, of course, make mistakes with this code, but those mistakes are much easier to spot. There's far less code to write and to maintain. Another example is in general induction. So mathematical induction is a general method of defining a sequence or defining some function that depends on a sequence, where you specify the base case and you specify the induction step. And the base case means what happens when the sequence is empty or has just one element or something like that. And the inductive step is how to compute the next value given the previous value of some kind. And this is exactly implemented by the function fold left. So for example, if you want to compute the mean value of a sequence, which means we need to compute the sum of all values and divide it by the length of the sequence. But we want to do this in a single pass. We do not know in advance the length of the sequence. We want to go through the sequence and count its length and count the sum in a single pass. So this is implemented using a fold left, where you start with the induction with the base case, which is the sum equal to 0 and the length equal to 0. And you update if you have a previous sequence with a given sum and a given count. You have a new element, then you add this element to the sum and you increment the count. And the result will be a pair of sum and count, which you pipe into this function. Pipe is a Scala operation that puts the argument into the function. So the argument is to the left of the pipe, this is the argument, and the function is to the right of the pipe, this is the function. Sometimes this is a useful syntax. So then you have done this in a single pass. We do not write loops explicitly, we do not have an index of the loop, we do not increment the index, we do not access the sequence, none of that is written explicitly, but of course when this is run, the compiler will do all that work, will make a while loop or something like that. The programmer does not need to look at that low-level code. This is the main advantage of having this feature of loop-free iteration. And any inductive definition can be converted to a fold, and this function is very general. So in other words, we have covered the entire class of problems that are defined inductively. Take a sequence, create a new sequence, take a sequence, create a number out of it, take a number, create a sequence out of it. All of these problems are covered without writing loops. There are many other applications of this technique. These functions that you need to use, map, filter, fold, and so on, these could be implemented in very different ways. For example, asynchronously, in parallel, distributed across many computers. But your program still looks like that. It still looks like a sequence of operations like this. Under the hood, the compiler will translate that into very complicated code that could run on a cluster asynchronously in parallel, but this code will not become more complicated to write. This style is called map, filter, reduce style of programming. And in order to support this style of programming, the programming language must have certain features, which most programming language today have. And one of these features is that you need collections with user-definable methods, such as you need to want to define map, filter, and reduce on new custom collections or on many different collections. Second necessary feature is that you need to be able to pass functions as arguments to other functions. So this is an example where you have an updater function that describes how the next step is computed from the previous values. This is a function that needs to be passed as an argument to the function fold left. And similarly here, the function here is passed to map. The function here is passed to filter. This is a feature that is necessary. So functions that are passed as parameters to other functions need to be easily written. They have to be short expressions, and they're called lambdas sometimes, but this of course doesn't help to understand what that is. These are just nameless functions, functions that are defined without defining a name for them. They're defined inline and used usually only once, so there is no reason to define a name for them if a function is only used only once. So this feature, the nameless functions or lambdas, or they're called by many different names, this feature in different languages, this has been so important and so useful that pretty much every programming language added that feature around 2010 to 2015. You can look at when this was done in C++, in Java, in other languages. They all added this feature. Even JavaScript, it had syntax for this feature, which is easier. And the third feature that is necessary is to work with tuple types. So tuple types are types like this, where you have several values put together, but there's no name for this type. It's just an automatically created type that has this pair and then this thing over there. Integer, integer, integer could be, for example, or double. In this case, it's double, 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 or integer. And again, this is a feature that you can create and use these values without creating an extra name for the type or class that has this data. So if you had to create a name, the code would become much longer. So this feature is convenient. It's not required, but it's very convenient. So if you don't have this feature, if you don't have lambdas, you have to write name for each function separately somewhere else. You define that function and then you pass it as a parameter. Or if you don't have the tuple type, so first you have to define a class, like in Java, for example, you have to define a class that contains these things, and then you pass the name, and so on and so on. Your code becomes very, very difficult to write. So unless you have these features, you cannot very easily write code in the map filter reduce style. So this is the first feature that brings a lot of advantages in many problems, many domains, such as big data, pipelines, and most programming languages today support map filter reduce style in one way or another. The second feature of functional programming is type parameters. So, for example, you have an array, and you can specify that it is an array of integers. And then the compiler will check that it is always integer in the array. You cannot put a different value, like a string, for example, in the array. And if it's an array of string, then you could not put integers into that array. And because the types need to be parameters, so array should be defined for any type of its elements. So for example, the type could itself be array of something else, and that type could be a tuple of int string, for example. So then you can have a complicated type, such as array of arrays of pairs of integers and strings. The language should support that. So you could have types of any complexity like that. And the decisive advantage for the programmer comes from the fact that all these methods that we just saw, like map, flat map, zip, and so on, they use the types and they change the types in some way, but the compiler can check that the types are correct. So for example, here's a computation where you convert some sequence into another sequence, zipping it with this, and then computing some kind of string out of that. At each step, the type of the intermediate result is checked by the compiler. So initially you have a sequence of integer, then you have a sequence of pairs of integer string, and then at this point the compiler will check that you are taking a pair of integer and string here and not something else. And then it will become a sequence of string. So when you use this expression, the compiler will check that you're using it correctly as a sequence of string. This is a very important feature that prevents many errors of oversight on the part of the programmer. So these long sequences of chained operations can be very safe because at every step, intermediate sequences are being checked for types. And this is done at compile time. So your program will not even compile unless all the types match. Another advantage of this feature is that you can write code parameterized by types. You can write this code once and then you can use it with different type parameters. Here's an example. You have a function called map that takes a sequence of type A, takes a function from A to B, and it returns a sequence of type B. Now this is a standard function which one uses in the MapReduce style of programming, but A and B are arbitrary types. So the same function, the same code is written once in the library and it's being used with all kinds of types, A and B. Many programming languages have this feature of having type parameters and being able to write code once with type parameters and then using that code many times with different specific types set instead of type parameters. Java added this feature in 2006. C++ can imitate this feature with templates. Golang decided that this feature was not necessary and now is regretting that decision as far as I heard, and they might get type parameters in the future. All the languages of functional programming have this feature. The third feature of functional programming is what I call disjunctive types. Now this is not a very well accepted name, but I use this name for specific reasons. An example of a disjunctive type is enumeration type, or enum, and in Java it looks like this, and it describes a set of disjoint possibilities. So this value could be only one of these three and nothing else. Now this is a very limited kind of disjunctive type, and it needs to be enriched. So functional programming enriches this feature in that each possibility can additionally carry values of some types, extra values. Here's an example. I'm using the syntax of a future version of Scala 3, which will look like this. So it's very similar to Java, except that, well, you have these case words here. That's just syntax. But the important thing is that each of the cases could carry additional data. So this case carries no additional data, but this case carries a value of type float. So in this way, you can represent much more sophisticated data which can be either, for example, no roots or one root of an equation, say. The switch operation that is present in Java to deal with the enum is also enriched, and it extracts this data from disjunctive values. So for example, if you have a value roots of this type, then you write a statement which looks like this. It's a switch statement essentially, but it is enriched in that it matches the value that is carried by this enum into a new variable, x, which is called a pattern variable. And then you can use that pattern variable in this case, but you cannot use it in another case. So it's a very safe kind of switch statement. If the value is like this, and there are only two cases here, you can only have this or this case. So if it's like this, you get the x and you can compute some expression using that x. Otherwise, you cannot possibly, by mistake, use some kind of wrongly defined variable. If you have no roots, there's no value that you can use in any further computation in this case. So mathematically speaking, a disjunctive type describes a value from what is called tagged union. It's a union of sets but each set in the union is tagged by a name. And these names are, for example, one root and no roots. And these names make it impossible to make a mistake as to from which part of the union a certain value comes. Now, this is a set of all float values. And this is a set that just contains a single value, no roots. There's no data in it. So there's a single value, which is no roots. And this type is a tagged union, which is either a float value or a special value, no roots. So there's no mistake that you can make while working with this type. So these are the features that programming languages like standard ML, OCaml, Haskell, F#, Scala, Swift, Rust, and so on. They all have this feature, which is disjunctive types and pattern matching. So pattern matching is very convenient and makes it completely safe to write switch statements with disjunctive types. But this feature is not supported in languages such as C, C++, Java, and so on. It's not supported in relational programming languages like Prolog, SQL, Datalog, and so on. It's not supported in configuration data formats, XML, JSON, YAML, and so on. So if you want to serialize a value of this type, it's kind of not easy in these formats. You can serialize using libraries, but under the hood they use some tricks, and because these formats were not designed to handle disjunctive types. And in fact, only programming languages designed for functional programming always have this feature. There are very few other programming languages that have the same feature. One exception is Pascal, that has variant records. Another exception is Ada, that also has some kind of variant records. A very powerful feature that allows you to handle all kinds of complicated domains with corner cases with complete safety. Another thing that is important about having disjunctive types is that it makes the type system logically complete. Now, this is a purely theoretical and mathematical property, but it turns out that this logical completeness has specific practical advantages. And what is this logical completeness? Consider the possible types, type constructors that you can have, say in Scala. There are tuples. There's the either type, which is the standard disjunctive type. There's a function type. There's a unit type and a nothing type. The unit type has only one value. The nothing type has no values. If you think about when you can have values of these types, then you will find that you can have a value of the tuple only when you have both values of type A and type B. So this is a logical conjunction, which is notated in logic like this. If you have a value of type either AB, it means a logical disjunction. You have a value of A or you have a value of B, which is notated like this. If you have a function from A to B, it doesn't mean you have an A or you have a B. It means if somebody gives you a value of type A, then you can compute a value of type B. And that's a logical implication. If somebody gives you an A, then it implies that you can have a value of type B. So that's denoted like this in logic. The unit type is always, it has a single value which you can always compute. You don't need any data to compute that value. So this is like a logical true value, which is always true. We don't need any other information to conclude that it is true. And the value nothing is like a logical false. It can never have a value. So if you are asking a question, when can I have a value of this type? Then the answer will be, it's a logical operation of the types A and B that you're using. Now, on the right, I have shown a type notation that I'm using to denote these type constructions. This type notation is designed to reason about types. It's completely equivalent to code, but it will be different syntax in different languages. So if you use the type notation, then you can unambiguously translate that into types in specific language syntax. And it turns out that if you don't have one of these operations, for example, disjunction in the logic, then the logic is incomplete. The logic is incomplete in mathematics when there are some theorems that you cannot prove using the allowed logical operations. And this is, of course, a pity. You should be able to prove them, or you expect to be able to prove them, but you can't because you're lacking some new operation that you maybe don't know about. So programming languages that have conjunction but do not have disjunction are not able to express certain business logic very easily. And that is apparently not obvious, so almost no other programming languages decided to have this feature. But all the functional programming languages have realized that there is a logical side to this reasoning and that it's better to have a complete logic, mathematically complete logic. And actually this makes for easier programming. Programming have fewer errors because errors you can model using different cases, or you can have not necessarily errors but various corner cases which are not easily representable using numbers, say. All of that becomes very safe and expressive program if you use disjunctive types. So a type system that has all of these 5 constructions is called a Hindley-Milner type system. Oh yeah, and type parameters, of course, need to be there as well. And so functional programming languages, OCaml, Haskell, F#, Scala, Swift, Rust, and so on, they support all these constructions. And so they have a complete logic of types. Finally, the 4th feature of functional programming is chaining of effects. To motivate what that means, let's consider computations that can fail with an error. To model this, we use a disjunctive type. In Scala, there's a standard disjunctive type, which is try. And this is equivalent to an either of throwable and a value of type A. Now, throwable is a class in Java that describes various information about the error, up to the line in your code, in your file name, where the error occurred, which function was called, and so on, and the message of that you could add to this, and so on. They're very rich information that is encapsulated by this type. So instead of throwing an exception and crashing the program, you can catch the exception into this disjunction of error or success. So that's going to be in Scala a disjunction of failure and success. So working with this type requires code patterns that time and again show up. The first of them is that you create this value, which could be an error, and then you want to use that. If it's not an error, you want to use that value in a computation, and that computation does not fail. So it's some function from A to B that never fails. So then you want that success of A is transformed into success of f of A, but failure of some t, where t is a throwable, remains unchanged. So that's what you want. And the second pattern is that you have an initial value which could fail, and you have a computation that also could fail. And if the initial value fails, then you don't have a value of type A, so you don't do this computation. But if you have a value of type A, say you have success of A, then you compute g of that A, which could fail, and you return that. So that becomes a try of B. That is a very often used pattern, because then you can compose different computations that can fail, and you stop at the first failure. The first failure occurs, you cannot continue because you don't have a value to continue with. And if everything goes well, you continue. So if all of the steps succeed, then at the end you have a success of something. But if you have any failure, then you have a failure, the first one stored. So that's a very often used pattern. So how do you implement that pattern? Well, you can use a match statement, obviously. A match expression, you write it like this. So suppose an example, you get the file statistics and then you extract timestamp from those statistics. Now, getting the file statistics could fail because the file could be not readable, the disk could fail to read or whatever, file could be missing. But once you have the statistics, then you get the timestamp always without failure. There's always this timestamp in the statistics. So you write code like this. So if it's a success, then you return a success of this timestamp. And if it's a failure, then you just keep that failure. And that's the first pattern, using in a computation that cannot fail, and then using the try in a computation that can fail. An example is you open a file, and then you try reading that file. Now, if you open a file, that could succeed, but then you try reading that file and it fails for whatever reason. So you have to try again, and that could fail. So that could return a try of, say, array of byte. Note that here we're using this nested type parameter feature. Or if it's a failure, you return a failure. So that is the example of a second pattern. And you can combine these patterns at will. So here's an example. You read a file, you decode its text in UTF-8, and you count number of characters. So first you have this opening, which could fail. If it succeeds, then you try reading it, which could fail. If it succeeds, then you decode UTF-8, which could fail. If it succeeds, then you return the length. And otherwise, you just fail, you keep failing. Now, this code, I believe there might be a mistake here. It could be probably not a file name here, but file, well, it doesn't really matter. I will fix that in the slides. The point is that this code is quite awkward. It's deeply nested and repetitive. And by the way, this sort of code is common in Go language, where it is a pattern that functions return an error and the result, and then you're supposed to check whether the result is nil or not. And then if it is not nil, then you have a result. Otherwise, you don't. You need to look at the error. And then you continue. So you try read, and then again you get an error or a result, and so on. So this kind of nested repetitive code is unavoidable in the Go language. And notice that the Go language returns a pair of error and result rather than returning a disjunction, which logically it is a disjunction. You either have an error or a result. But here you have both error and result because you return a pair, because the Go language does not support disjunctive types. The result is that you could by mistake return both an error and a result, and the program will fail in difficult to debug ways. The program does not guarantee that only one of them is returned and that the other is nil. There is no guarantee. The compiler cannot guarantee that. So that's why in Go language, not only you have to do repetitive and deeply nested code like this, but you are writing code that is error prone. It's easy to make a mistake. So this is why it has real costs if your programming language does not have a complete logic of types. It does not support disjunction. You will be doomed to writing code like this. But are we doomed to writing code like this? This is, of course, safe. but repetitive and nested. So this is a situation where we chain computations having an effect. Now, an effect is not side effect here. It is not the same as side effect at all. Effect means you have extra possibility of having extra information other than your main result. So this extra information could be of different kinds, and it's encapsulated by a type constructor. So the meaning of effect here is that you have a type constructor. You don't return an int, you return a try of int. Now what that is depends on the type constructor. But that's the only meaning of the word effect here. It's not side effect, it's not some kind of magic. It's just that your function takes a type, such as string, and returns the result of type int wrapped into a type constructor, wrapped into it in a type constructor. So that's the only meaning of the terminology effect, effectful computation. It's a computation that returns a type constructor applied to your type of the result. So how do we avoid repetition and nesting? We use map and flat map. So it turns out you can define map and flat map for the try class. And the result is that you have a computation that looks like this. So you take a try and you map it with f in case it cannot fail, or you flat map it with g in case it fails. The Scala library actually helps you, and if f and g throw exceptions, these exceptions are caught as well in the try. So this is completely safe. It will never fail to compute this, unless you fail to have f, of course. The functions fmap and flm have slightly different type signatures, and these are used in functional programming reasoning. They're more useful for reasoning than for practical coding, because they have this kind of nice structure. A to B goes to try A to try B, A to try B goes to try A to try B. This kind of symmetric structure of the type signature is easier to reason about, but they're not particularly convenient in writing code. It's much more convenient to write code like this with .flat map and .map. But these are the functions that you can implement once in your library and then reuse. And then your pattern will become that you map this with a function that gets a timestamp, or you flat map this with a function that reads a file. Instead of writing match case statements, now expressions, you now write .map.flat map. So here's what you would do. For example, you combine a function that returns a try with another function that does not, and you combine a function that returns a try with another that also returns a try. So these combinations can be used in any way, in any order, and then you get a very powerful way of combining computations that fail, that has no nesting and no repetition. All the nesting and repetition is hidden in the code of these functions in a very clever way. So this looks like some MapReduce style of programming, but there is a better syntax for it, which is that you write this kind of code, which looks like a loop. For suggests a loop for programmers who are familiar with languages like C and Java, but this is not a loop. This for has nothing to do with loops. It's a for yield construction, which is a block that is translated in a special way into calls of map and flat map. Namely, this arrow is translated into a flat map, and this is translated into map, and the last arrow is also translated into map. That is necessary to fit the types, otherwise types would not match. So now if you look at this syntax, it's kind of resembling a syntax for nested loops. Like this would be a syntax for nested loops, which you even can have in Python. But these are not loops, because try does not have many values inside it that over which you loop. Try could have at most one value, or it could just have an error, which means you stop this entire thing and return this error. So it looks like you're having nested loops over collections that only could have at most one element in them. It's kind of a very strange, degenerate kind of loops. But they have the same properties as nested loops, formally speaking. And so this is a very, very general syntax that works for many situations. It also works for nested loops. It works for try. It works for asynchronous computation with futures. It works for all kinds of effects to chain them. And the very similar syntax is available for other languages like Haskell, which is called do notation in Haskell. And in F#, this syntax is called computation expressions. So this syntax makes it much easier to write code, because this is what you would write for this program that decodes the UTF-8 characters. You would write code like this, which is very easy to write and to read. You try open file. Now it's kind of easy to see what's happening. You get a file. You try reading that file, you get bytes. Try decoding these bytes, you get decoded array, and then you get the length of that string. And then the result is length. Now the result is going to be try of this length value. So it could actually fail if any of these operations fail here in the middle, but it could succeed. So that is the advantage of the special syntax. Your programs not only are completely safe, you cannot possibly forget to handle one of the errors in here. They're all automatically handled correctly. The first error will break this entire computation and stop it and return that error value. You could not possibly forget to do that when you write this code. So whole classes of stupid errors, so to speak, are completely impossible if you write code like this. Although this feature is so useful, it is kind of difficult to learn initially for programmers who never saw this kind of style of coding. This style of coding requires some learning, but it has significant advantages. And so this is the fourth feature of functional programming. All of these features can be combined in any way you want. And the main advantages of functional programming come from combining them. You can use functional methods on collections that have type parameters. These collections could contain values of disjunctive types, and so they represent your program requirements very expressively and without forgetting any corner cases. And when you work with these collections, you avoid explicit loops, you make sure all types match, and at high level you can compose such programs by chaining effects. So an effect could be, for example, parallel computation, asynchronous computation, computation with error, computation in an array, or any combination of these. So for example, you could have a computation that occurs asynchronously, can return an array of values, or could fail and could return several failures, which you all want to keep and examine later. So these are the reasons why functional programming gives so much advantage that today many languages want to adopt some of these features. Loop-free iteration, type parameters, disjunctive types, and chaining syntax. These are the most beneficial features of functional programming that require the least amount of learning to be able to use. There are more advanced features of functional programming, which I'm not talking about in this tutorial, because these features have a lower cost to advantage ratio. You have to learn more to be able to use those features effectively, but you will use them much more infrequently, much less advantage that comes from knowing about those features. The first four that I'm talking about are features that shared between most functional programming languages. If you know how to use those features in one language, you know how to use them in all other languages because they work in exactly the same way. Only the syntax is different. You need to learn the syntax of a new language, and that's it. You already know how to use loop-free iteration using the map filter reduce style. You know how to use type parameters. You know how to use disjunctive types with pattern matching, and you know how to use the chaining notation, do notation, for yield notation, or other such notation. And you already know how to write programs in this style. And non-FP languages, I'm putting this in quotes because it is not clear what it means to have an FP language really, but I'm saying that these are the four essential features that if you have in your language, you can use to great advantage. And if you don't have these features, you can still emulate the same thing, but your code will become longer, it will be harder to read, and it will be easier to make a mistake in that code. In other words, the cost of the use of these features is higher if your programming language does not support these features directly. So that is why you could say programming languages that support at least these four essential features directly, those are the real functional programming languages today. And that would include Swift and Rust, for example, although they're very different from Haskell and Scala or Elm or OCaml, but all of these languages have a common ground. They have a complete logic of types. They have these four essential features that already give you so much advantage over procedural style or object-oriented style that writing programs in this way is much more productive. This ends the tutorial.